Listen, when the grid goes down, and I mean really goes down, not just a thunderstorm knocking out power for 6 hours, there's going to be a very short window where the rulebook gets thrown out the window. The electrical codes, the safety regulations, the permits, all those things that keep modern society from burning itself down, gone. And in that chaos, the people who know how to bend the laws of physics without breaking them, who understand the forbidden engineering tricks that get you arrested in peacetime but keep you alive when everything collapses, those are the ones who survive. These aren't the skills they teach you in YouTube DIY videos or home improvement shows. These are the techniques that utilities companies don't want you to know, that code enforcement would slap you with fines for attempting, and that most engineers would never admit they understand. But here's the truth. Every single one of these methods is based on sound physics and real-world application. They're just illegal under normal circumstances. So let's talk about what happens when circumstances stop being normal. First thing you need to understand is that electricity doesn't care about your local ordinances. It follows the path of least resistance whether you have a permit or not. And when the grid fails, whether it's from an EMP, a cyber attack, or just cascading infrastructure collapse, you're going to need power. Not want it, need it. Because without electricity, you can't purify water efficiently, you can't preserve food, you can't communicate, and in winter, you can't survive. The average home has about 3 days of food, but without refrigeration, that drops to maybe 1 day of edible supplies. Your freezer becomes a biohazard within 48 hours. So here's the first forbidden trick: backfeeding your house through a dryer outlet. Now, before you panic, yes, this is wildly illegal, and yes, it can kill linemen if done wrong, which is exactly why you never ever do this while the grid is functioning. But in a true grid-down scenario where power isn't coming back, this knowledge becomes survival critical. You take a generator, you create what's called a suicide cord, a male-to-male extension cord that every electrician will tell you should never exist, and you plug it into your dryer outlet. This bypasses your main breaker and backfeeds power into your home's electrical system. The reason this works is because your dryer outlet is 240 volts, which matches most generator outputs, and it's a direct line into your breaker panel. But here's the critical part that keeps you alive. You must, absolutely must, flip your main breaker to the off position first. If you don't, and the grid suddenly comes back online, you're feeding generator power back into the utility lines, which can electrocute workers trying to restore power miles away. In a permanent collapse scenario, this isn't an issue, but the technique itself violates every electrical code in existence because of the suicide cord. That cord can energize both ends simultaneously, meaning you can grab what looks like an innocent plug and receive a lethal shock. This section is based on practical field survival experience rather than formal academic sources. Now let's talk about water, because electricity is only half the equation. In a grid-down situation, municipal water treatment fails within days. The pumps stop, the chlorination systems shut down, and what comes out of your tap, if anything comes out at all, becomes a biological weapon. Cholera, dysentery, giardia, cryptosporidium, all the diseases that killed our ancestors before modern sanitation. You need to purify water, and boiling it uses an insane amount of fuel that you probably don't have. So here's the second forbidden engineering trick: building a UV sterilization system from salvaged components. You know those UV lights they use in HVAC systems and reptile tanks? Those emit UVC radiation at 254 nanometers, which is the exact wavelength that destroys DNA in bacteria, viruses, and parasites. The reason this is forbidden knowledge is because UVC exposure will absolutely destroy your eyes and skin. It's the same radiation that gives you sunburn, but concentrated and unfiltered. Commercial UV water purifiers are heavily regulated because of this danger. But in a collapse, you can build one from a salvaged UV bulb, a piece of PVC pipe, and a quartz tube. The quartz is critical because regular glass blocks UVC. You run your water through the tube with the UV bulb inside, and the radiation nukes everything living in the water. Flow rate matters. Too fast and the exposure time isn't long enough, too slow and you're wasting energy. The math is simple. For effective sterilization, you need about 40 millijoules per square centimeter of UV exposure. A typical 15-watt UV bulb puts out enough radiation to treat about 2 gallons per minute if your tube diameter is correct. The danger is in the handling. If that bulb breaks, you're exposed to mercury vapor. If you look directly at it while running, you can literally cook your corneas. But when the alternative is drinking water that gives you bloody diarrhea until you die from dehydration, suddenly those risks start looking acceptable. Here's where it gets darker. Food preservation without refrigeration becomes the defining challenge of long-term survival. Your ancestors did this with salt, smoke, and fermentation, but there's a faster, more efficient method that's technically illegal in most jurisdictions because it involves chemicals that can be weaponized. We're talking about building a food dehydrator using lye and forced air. Sodium hydroxide, or lye, is the same chemical used in drain cleaner, and it's terrifyingly caustic. It will dissolve organic matter, including your skin, your eyes, and your throat if you're careless. But it's also used in commercial food processing to cure olives, make pretzels, and in some cultures to preserve fish. The trick is using a very dilute solution. We're talking 0.5% concentration to quickly strip moisture from vegetables and meat without cooking them. You build a chamber where you can control airflow, you dip your food in the lye bath for seconds, not minutes, then you blast it with dry air from a fan. The lye breaks down the outer cell walls, which allows moisture to escape exponentially faster than regular air drying. A piece of meat that would take 2 days to dry in the sun can be preserved in 6 hours. The engineering challenge is controlling the concentration and exposure time. Too strong or too long and your food becomes toxic. Not strong enough and you're just making mold habitat. The reason this is forbidden is obvious. Lye is a hazardous chemical, and mishandling it can cause horrific burns. Plus, in the wrong hands, the knowledge of how to concentrate and weaponize caustic substances becomes dangerous. But in a post-grid world where your options are preserve food or starve, this chemistry becomes essential. This section is based on practical field survival experience rather than formal academic sources. Let's shift to heat, because winter in a grid-down scenario is a death sentence for most people. Your furnace needs electricity to run the blower, your gas fireplace needs electricity for the ignition system, and even your wood stove becomes less efficient when you can't circulate the air. Here's the fourth forbidden trick: building a rocket mass heater in your basement. This is illegal in almost every jurisdiction because it violates building codes, fire safety regulations, and insurance policies. But it's also one of the most efficient heating systems ever designed. The principle is simple. You burn wood in a J-shaped combustion chamber that creates an extremely hot, clean burn. We're talking 1800 degrees Fahrenheit. That heat gets pulled through a thermal mass, usually a long channel filled with cob or brick, which absorbs and radiates the heat slowly over hours. A properly built rocket mass heater can heat a home for 24 hours on an armload of wood, compared to a traditional fireplace that might give you 3 hours of heat from the same amount. The reason it's forbidden is because it requires drilling through your foundation. It creates extreme temperatures that can crack concrete if built wrong, and if you don't understand the fluid dynamics of the draft system, you can fill your house with carbon monoxide. But the engineering is sound. You need a vertical feed tube that creates a natural draft, an insulated burn chamber that reaches temperatures high enough for complete combustion, that's why there's almost no smoke, and a thermal mass with enough surface area to radiate heat without creating hotspots that crack the material. The math on heat transfer is beautiful. A cubic foot of cob can store about 30 BTUs per degree Fahrenheit. If you heat it to 200 degrees and let it cool to 70 degrees, that's 3,900 BTUs per cubic foot. Build a mass with 50 cubic feet and you're storing 195,000 BTUs, which is enough to heat a well-insulated room for a full day. The danger is in the construction. If your draft isn't right, you create backdraft and die from smoke inhalation. If your thermal mass isn't properly supported, it can collapse and crush someone. But when the alternative is freezing to death, these engineering challenges become solvable problems. Now we need to talk about communication because isolation kills, just as surely as cold or hunger. When the grid collapses, cell towers last about 8 hours on backup batteries, then they're dead. Internet? Gone. Your ability to know what's happening 10 miles away drops to 0. Here's the fifth forbidden trick: building a long-range radio transmitter from salvaged parts. Under normal circumstances, operating an unlicensed radio transmitter is a federal offense. The FCC does not play around with this. But in a true collapse, those regulations become meaningless, and the ability to communicate over distance becomes survival critical. You can build a basic AM transmitter using a car alternator, some copper wire, and a transistor from old electronics. The principle is elegant. You create oscillations in an electrical circuit at a specific frequency, you modulate those oscillations with your voice, and you pump it through an antenna. Range depends on power and antenna height. A 100-watt transmitter with a quarter-wave antenna mounted 30 feet up can reach 20 to 50 miles depending on terrain. The engineering challenge is tuning the circuit to a frequency that isn't jammed with interference, and that requires understanding resonance and impedance matching. Your antenna length must be mathematically related to your wavelength. For an AM signal at 1 megahertz, your wavelength is 300 meters, so a quarter-wave antenna needs to be 75 meters or about 246 feet. That's impractical, so you use loading coils to electrically lengthen a shorter antenna. The danger is twofold. First, high-power RF radiation can burn you if you touch the antenna while transmitting. Second, if you're broadcasting, you're announcing your location to anyone with a receiver. In a hostile environment, that can be fatal. But the ability to coordinate with other survivors, to share information about threats or resources, to maintain some fragment of organized society, that's worth the risk. This section is based on practical field survival experience rather than formal academic sources. Let's talk about the elephant in the room: security. In a prolonged grid-down scenario, the thin veneer of civilization peels away fast. The first wave is panicked civilians grabbing what they can. The second wave is organized looters who understand that police response is gone. The third wave is the truly desperate, and that's when things get medieval. You need perimeter security. And here's the sixth forbidden trick: building early warning systems using piezoelectric sensors and scavenged electronics. Piezoelectric materials generate electrical voltage when compressed, and they're everywhere, in lighters, in speakers, in old landline phones. You can create pressure sensors by burying piezo elements under pathways or at choke points. When someone steps on them, they generate a voltage spike that can trigger an alarm or light. The engineering is straightforward. You need a circuit that can detect a small voltage change and amplify it into something useful. An old transistor radio can be gutted and repurposed as an amplifier. You run wire from your sensors to a central monitoring point, and suddenly you have a perimeter system that tells you when someone's approaching. The reason this is forbidden knowledge is because the same principles apply to more lethal defensive systems, and nobody wants to publish instructions for building booby traps. But early warning doesn't harm anyone. It just gives you time to respond. The mathematics of sensor placement matters. You want overlapping coverage so there's no blind approach, and you want them positioned where natural terrain funnels movement: a gate, a gap in a fence, a trail junction. The limitation is power. These systems need batteries or a small solar panel to stay active, and maintenance, because weather and corrosion will kill exposed electronics. But knowing someone's coming before they know you know they're coming, that asymmetry is worth its weight in ammunition. The seventh forbidden engineering trick is one that most people don't even realize is possible until they're desperate: extracting fuel from abandoned vehicles. When the grid goes down and gas stations can't pump, every car on the street becomes a potential reservoir of energy. But here's what they don't tell you. Modern cars have anti-siphon devices in their fuel tanks specifically designed to prevent theft. You can't just stick a hose down there and suck anymore. The engineering workaround involves understanding fuel system architecture. Every car has a fuel pump inside the tank, and that pump has an inlet and outlet. If you can access the fuel line between the tank and the engine, you can splice into it and use gravity or a manual pump to extract fuel. The easiest access point is usually under the rear seat or through the trunk where fuel lines run. You need to know which line is the feed line versus the return line. Feeding fuel back into the tank doesn't help you. The danger is obvious. Gasoline vapor is explosively flammable, and one spark from metal-on-metal contact or static electricity can turn you into a fireball. You need to work in ventilated areas, use non-sparking brass fittings, and ground yourself to discharge static. The chemistry of gasoline degradation matters too. After about 6 months, the lighter hydrocarbons evaporate and the remaining fuel becomes gummy and useless. You can extend this by adding fuel stabilizer, but in a long-term collapse, you're racing against chemistry itself. A typical sedan holds 12 to 16 gallons. In a neighborhood with 100 abandoned cars, that's potentially 1,500 gallons of fuel if you can extract it before it goes bad. That could run a generator for months, power vehicles for evacuation, or trade for other resources at extraordinary value. The reason this knowledge is forbidden is because fuel theft is a serious crime, and teaching people how to defeat anti-siphon systems enables criminal behavior. But when those cars are abandoned and their owners are long gone, the moral calculus changes completely. Here's number 8, and this one gets into territory that makes even hardened preppers uncomfortable. Building a methane digester from household waste. Human waste, food scraps, animal manure, all of it produces methane gas through anaerobic decomposition. And methane burns. It's the same natural gas that heats homes and powers stoves, just produced on a small scale. The engineering is medieval in its simplicity, but sophisticated in its biology. You need an airtight container where organic matter can decompose without oxygen. Bacteria break down the material and release methane, which you can capture and compress for use. A 50-gallon drum can process waste from a family of 4 and produce enough methane to cook 1 meal per day. The chemistry is temperature dependent. Mesophilic bacteria work best at 95 to 105 degrees Fahrenheit, while thermophilic bacteria need 135 to 145 degrees, but produce gas faster. In cold climates, you need to insulate your digester or bury it below the frost line. The forbidden aspect is twofold. First, handling human waste carries serious health risks. Hepatitis, E. coli, parasites, and any mistake in the process can spread disease. Second, methane is odorless in pure form, but it's also asphyxiating and explosive. Natural gas companies add mercaptan so you can smell leaks. Your homemade methane won't have that warning smell, which means a leak in an enclosed space can suffocate you before you realize anything is wrong. The engineering challenge is maintaining the right carbon to nitrogen ratio in your feedstock. About 30 to 1 is optimal. And monitoring pH levels. Too acidic and the bacteria die. Too alkaline and you get ammonia buildup. But the payoff is legitimate. You're turning a waste disposal problem into an energy source. Every pound of organic matter you process is 1 less pound attracting rats and spreading disease, and you're getting cooking fuel in return. The Romans understood this in a crude form. We've just refined the process with modern materials and microbiology. This section is based on practical field survival experience rather than formal academic sources. Number 9 gets into metallurgy, and this is where survival engineering becomes genuine craftsmanship, building a forge from scavenged materials to work metal. When things break in a grid-down world, you can't order replacement parts on Amazon. You need to forge them. A basic forge needs 3 components. A fire chamber that can reach 2,500 degrees Fahrenheit, forced air to achieve that temperature, and a work surface that won't crack under thermal shock. You can build the fire chamber from fire bricks salvaged from old kilns, furnaces, or even barbecue grills if you stack them right. The forced air comes from a hairdryer or a hand-cranked blower from old blacksmith equipment. The work surface is where it gets interesting. You need an anvil or anvil substitute with enough mass to absorb hammer strikes without ringing or bouncing. A section of railroad track works surprisingly well. It's hardened steel with a flat working surface. The physics of forging is about heat and deformation. When steel reaches orange-red heat, about 1600 to 1800 degrees Fahrenheit, its crystalline structure becomes plastic. You can hammer it into new shapes, and when it cools, it retains that shape. This lets you repair tools, create blades, fashion hinges, make nails, all the small metal components that hold a functional existence together. The reason this is forbidden knowledge in modern society is because forging weapons violates laws in many jurisdictions, and the skills to work metal are the skills to make anything, from a knife to a gun barrel. But the same techniques let you repair a broken shovel or forge a new hinge for a door. The danger is severe burns, carbon monoxide from the forge fire in enclosed spaces, and metal fragments from grinding or hammering that can blind you. You need eye protection, leather gloves, and respect for the fact that metal at forging temperature looks almost identical to metal that's merely very hot. Both can char flesh instantly. But when your axe breaks and you need to split wood to stay warm, the ability to forge a new axe head from scrap steel becomes the difference between survival and slow death from exposure. The 10th and final forbidden engineering trick is perhaps the most dangerous:
building electrical storage from salvaged lithium batteries. Every laptop, every power tool, every electric vehicle has lithium-ion batteries, and when the grid is down, those batteries become currency. But lithium batteries are temperamental, violent things. They store enormous amounts of energy in chemical form, and if that energy releases suddenly through short circuit, overcharging, or physical damage, they don't just catch fire. They explode with jets of flame and toxic gas. The engineering challenge is harvesting cells from battery packs, testing them for capacity and internal resistance, and then reassembling them into larger banks with proper battery management systems. A laptop battery typically has 6 to 9 1865 cells inside. Each cell can store about 10 watt-hours of energy. Pull cells from 10 laptops, and you've got 600 to 900 watt-hours of storage, enough to run LED lights, charge radios, and power small devices for days. But here's where it gets lethal. Lithium batteries must be charged at precise voltages and currents. Overcharge them, and they enter thermal runaway, a chain reaction where heat causes more heat until the battery events flammable electrolyte and ignites. Undercharge them too many times, and you damage the chemistry permanently. You need a battery management system that monitors each cell individually and balances the charge. You can build this from Arduino boards and voltage monitoring circuits, but one mistake and you've built a bomb. The reason this knowledge is so restricted is obvious. Lithium battery fires burn at temperatures that melt aluminum and can't be extinguished with water. Water actually makes them worse by reacting with the lithium. And the toxic fumes from burning lithium include hydrogen fluoride, which will destroy your lungs. But in a grid-down scenario, electrical storage is everything. Solar panels are useless without batteries. Wind power needs storage. Your ability to capture energy when it's available and use it when you need it determines whether you have light, communication, and water purification. The mathematics of battery banking is precise. You connect cells in series to increase voltage, in parallel to increase capacity, and you never mix cells of different ages or capacities because the weakest cell determines the behavior of the whole bank. An electric car battery might contain 7,000 individual cells with a total capacity of 60 to 100 kilowatt hours. That's enough energy to run a modest household for a week. But extracting and repurposing that energy requires understanding chemistry, electrical engineering, and safety protocols that border on paranoia. So, here's the reality. These 10 forbidden engineering tricks represent knowledge that exists in the gap between legal civilization and raw survival. They're techniques that violate codes, regulations, and safety standards designed to protect people in functioning societies. And that's exactly why they matter. When the grid goes down, those protective regulations become meaningless. What matters is physics, chemistry, and biology. What matters is whether you can generate power, purify water, preserve food, stay warm, communicate, defend yourself, extract fuel, produce energy from waste, work metal, and store electricity. These aren't skills for weekend preppers playing at self-sufficiency. These are the engineering fundamentals that separate communities that survive from communities that collapse into chaos and death. The forbidding part isn't that the knowledge is secret. Most of it is documented in old technical manuals, military field guides, and engineering textbooks. The forbidden part is that using this knowledge under normal circumstances will get you arrested, fined, or sued into oblivion. But when circumstances stop being normal, when the systems we depend on fail catastrophically and permanently, this is the knowledge that keeps you alive. Learn it now while information is still accessible. Practice the safe versions where you can. Understand the principles so that when you need to apply them, you're not experimenting blindly in the dark. Because when the lights go out for real, there won't be YouTube tutorials or hardware stores or engineers to call. There will only be you, the resources you can salvage, and the knowledge you carry in your head. Make sure that knowledge is enough. Thank you.